Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my great pleasure to introduce Madhusudan Parthasarathi to you. Madhu is a professor at University of Illinois at Urbana-Champaign, and he has worked for many years on analysis tools for concurrency, and he has interests in automata theory and logics and program verification. Today he's going to tell us about a lightweight technique for monitoring concurrent programs.
Thanks. Okay, so I'm going to present this work on monitoring atomicity in concurrent programs, and this is joint work with a student at Illinois, Zadeh Farzan, who moved to be a postdoc at CMU and is now joining the faculty at U Toronto. Okay, so I will skip the introduction spiel, which I usually give. Because I'm at MSR. So essentially, with the advent of multi-core, there is this extremely vibrant research and possibilities for research in for multi-core programs, and of course, concurrent programs are it's not different, it's difficult, very difficult to test and verify. So one of the main things is that it's even hard to test a concurrent program against a particular test input. And the reason is because there are too many interleavings. And the chess project here is exploring ways to test this effectively in order to find bugs. But it's also, it's not just that it's hard to test, it's also hard to write and verify and make sure that you're actually doing something correct. I think this might be intrinsically due to the fact that we have a huge history of learning to think sequentially. Computational thinking has been synonymous with sequential thinking, and this might take quite a long time to change, even if we come up with the right paradigms for concurrent programming. So as we move to a concurrent world, it is much more likely that we're going to have a lot of errors, and finding these errors are going to be much more important probably than in the sequential world. Okay, so given that even in sequential program verification, it's very, very hard to come up with properties which the programmer can write in which he can verify specifications. The most work in concurrent for verification of concurrent programs has concentrated on what I call generic properties of correctness. All right. So the idea is that you do not have a real specification written down, but you have a generic specification which is common to all applications. Okay. It might be parametrized a bit to the actual application, but it's kind of general. So it's something like buffer overflows, right? It's something you don't, it's wrong by design, and you'd like to check for it. So, and one important property which is checked for is interference between the various threads in a program. So the thing noted is that most concurrency errors manifest due to interference between the threads that's not really meant, it's not really taken care of. And this is really the focus of research in people who are designing programming languages. Things like transaction memory and other things give you ways to control this interference, right? But there are also several other generic specifications other than transactions. The most important, of course, is the absence of races. Data races is a very important concern, not only because it can be an error, but also because the semantics of the programming languages like Java are not defined at all if you have data races in them, right? So they're clearly wrong, and you'd like to get rid of them. There is a new notion which has gained popularity in the last few years, and which is what I'll talk about, which is called atomicity, which essentially means that you have certain code blocks in your program, and you'd like those code blocks to occur atomically, not by semantics, but by it will be semantically atomic. It need not be actually executed atomically, but it will be semantically atomic. The idea behind this is that the same as for software transactions, is that usually people would like to do some piece of work on some part of the heap, and they would like to have complete control over it, and essentially think of that as a sequential part of the program, maybe a method. You'd like to think of it as sequential and completely avoid interference with the other parts of the program. As we will see in this talk, there are two notions of atomicity that seem to be robust and used, and those are causal atomicity and conflict serializability. So these two have been exploited, and I'll talk about both monitoring algorithms for both of these notions today. So there are other specifications as well. So the group by YY Zhu at Illinois did a study of various bugs in programs, and they also have a tool which does a different kind of property checking, which they call access invariants, which are kind of like atomicity specifications, but they are more data oriented. So they're more like linearizability with respect to small pieces of code rather than atomicity. Okay. So I've had the other presentation was in Keynote, and I could never manage to convert it to PowerPoint. So I'm actually going to switch between different slides and. Okay, so let me motivate atomicity a little bit and contrast it to data races. So a race is just an unprotected access to a shared resource by two threads, and one of them is a write. Right? So that's what a race is, and atomicity is quite different. So it's technically different, and it is neither stronger nor weaker than data races. All right. It is known that there were bug studies done, and it turns out that about 70% of the concurrency bugs that are reported in certain classes of programs, Apache servers and so on, are actually atomicity related bugs, in the sense that it's a very common paradigm to think about, and people try to put certain concurrency control mechanisms in order to ensure atomicity, and they often make mistakes in doing that.
Can you give us some example of non-atomicity related bugs?
Okay, so there are certain bugs. So for example, if I'm waiting for you to finish a task, so these are called ordering constraints in the same study by YY and others. So it turns out that about 25 to 30% of the errors are actually ordering constraint bugs, where I'm waiting for you to give the token to me, and people make mistakes because I might proceed without you going through. Yes.
So atomicity is a specification, right? So when you say bugs are happening because of atomicity violation, that means there is some atomicity specification which, when violated, will have the same behavior as this bug.
Yes. So we do not know. Yeah, that's what it means. So there is, if you look at the bug, it turns out that there is a part of the code which was where the programmer assumed that things are going to be atomic, and it wasn't.
And if you look at YY Zhao's paper, right, some of the ordering violations are actually can be considered as atomicity violations as well.
Okay, that might be true. It's very hard to actually say what what a bug is due to. It might be a combination of these two. So I just wanted to say that most bugs are atomicity bugs. And I think what you're saying is that maybe even more are. That's fine, yeah. So, and there has also been studies which show that if you use some notion of atomicity, then you actually find that most correct programs, most of them are actually atomic. So of course atomicity is not a required condition, but because you could handle very low level concurrency and still get things correct. So about 80% is of course is although atomic. So here's a simple example to tell you why data races are not enough to find all errors. So here's a simple program, and think of this as a method where I acquire a variable, the value of a variable, a global variable x, and I do some operations on it, and I update this variable, right? So this is race-free, even though the other thread is also using a synchronized access to a locked access to x. It is of course race-free, right? And I think this is this I think will be more common if we had data race checkers, which automatically told you something that there was a data race. I think the most natural thing the programmer would do if they don't care about the error, they will just want to test it, is that they will just use a synchronized block for every axis, right? And all data races will vanish, and none of the errors will vanish, right? So I think this shows why atomicity is a more high-level specification.
So does that mean that if somebody claims that their technique works better for data race-free programs, then basically that's a bogus claim?
Well, I don't know. I mean, maybe you can use this construct, the fact that it's synchronized, to do something else. That would not really mean that. Okay. So here's another thing where there is a data race, but it's okay because so for example, this is a read of x, and it doesn't really matter when I read x, and so there is a data race, but there is no atomicity violation there. Of course, that kind of program is bad because, again, the underlying memory model may not support even sequential consistency if you don't have data race-free programs. Yes?
With an argument list.
Oh, it's an... So, yeah, so I don't know if maybe there's a mistake, but basically this should really be an O-related operation, so that's wrong, yeah. It should be an O-related operation. So, okay, let's just assume that you acquire a lock specifically and release it, and that's called O. Okay, so let me move on. So the concept that atomicity can be a generic specification for concurrent programs was first proposed by Flanagan and Kadir in 2003, and so here's the definition of atomicity: is that I somehow make some parts of the code, sequential parts of the code, I mark them into blocks, and let me call them transactions. Okay? And this is not to be confused with transactional memory, where the semantics tells you that you will definitely have atomicity on that region. It's just an annotation which the programmer gives, or a tool automatically comes up with, which basically marks off pieces of code in your program, and that's called a transaction. Okay? Now, if I take a run of a concurrent program, I say it is atomic with respect to this marking, right? If there is an equivalent run in which every transaction is non-interleaved, right? So here's a run. I'm executing different events from various transactions, but there is an equivalent run where the transactions are serialized. Okay. So this is the general notion of atomicity, and depending on what you choose to observe, what your notion of equivalence is, and various other things, you get various different notions of atomicity. Okay. So here's the atomicity notion based on the database notion of serializability. So this is actually conflict serializability, which is the most popular notion of serializability because it's easier to check, even though it's a bit coarser than view serializability, which is probably a better mathematical notion. Okay, so what I assume is that all that I observe from a run are the read and write axes, right? So I have a set of entities over which I can read or write, and then I have 4 other tags. I have a begin end tag which tells me when a thread begins and when a thread ends, and I have those transaction begin and transaction end tags which tell me when a transaction within a thread begins and when it ends. Okay, so the view is that a thread executes multiple transactions, one after the other, right? And I observe all the reads and writes to global variables only that occur in the thread. Okay, so an event is really a thread doing one of these actions. And a concurrent run is just a sequence of events of that form, right? And as I said, I'll assume that they are well nested in the sense when you begin a transaction, you don't begin another again. You end it, right? So there are no nested transactions for now, and we'll just assume that. Okay, so then what we do is define a very natural notion of dependence between actions. The dependence tells you which are commutable actions or which are not commutable actions. So 2 events are commutable, are not commutable if either they belong to the same thread, or if one of them is a write and one of them is a read or a write of the same variable. So if you're accessing the same variable and one of them is a write, then they're not commutable. Okay. And with this notion of permuting events, I can now define the notion of equivalence of runs, right? So 2 runs are equivalent. Sorry.
You're not required the set of actions is not required to be finite or anything like that.
No, there's no.
So
yeah. So the set of entities is a countable set, and it can be anything. The set of threads can also be unbounded. Right. That's why we have this. So the equivalence of runs is defined as this as the smallest equivalence which satisfies the thing that 2 runs are equivalent if you can commute one pair of events, otherwise they are the same, then they are definitely equivalent. And you take the transitive closure of this definition, and you get the set of all equivalent runs. Okay, so is that clear? Okay, so it's a very simple, clean definition of what is equivalent to what. Okay, now this equivalence is actually sound in the sense that if you take a program and you take a run and you take another run which is equivalent to it, then that run is definitely equivalent in the sense that the actual values of the variables produced at the end will be actually the same as the other run. Okay, so 2 equivalent runs are same even without this abstraction, right, in the real program. And a serial run, which is what we need to do, is that all transactions are executed non-interleaved. Okay, so a run is atomic if I can find an equivalent run, according to this definition, where everything is serialized. Everything is serial. Okay, so that's the definition. Okay, so good. So what we are interested in is trying to monitor for serializability violations. So what we want to do is take a program, run it, and we want to keep track of whether there is an atomicity violation or not. Right? And it turns out that this is actually a well-studied problem in databases. And it depends on this. It relies on this graph called the conflict graph, which if you maintain, you will know whether there's a non-serializable run or not. The conflict graph was actually introduced in '76. It was done by Ishwaran, Gray, and others. It's a very classic paper, and there is in fact textbooks which tell you about how to do conflict graphs for detecting serializability. So let's look at what a conflict graph is through this example. Okay, so I have this run where the timeline goes this way. So first T begins and then reads a variable, and then the next transaction begins. The next thread begins and the transaction begins. It writes and reads X, and this one reads Y. So this is a new transaction. It reads Y, and then the first thread does a write to Y. Okay. So how do I'm monitoring this run. How do I make sure that it's actually serializable? Okay. So notice that, so these are the transactions. And notice that since this read X occurs before this write, in any serial run, I must definitely have that read occurring before the write.
I got a question. Supposing you have unfinished transactions in a run, what does it mean for such a run to be serial?
So we have a definition. Basically, you can think of it as an end transaction and say that everything
we just
occurs.
Make it ended arbitrarily at the last event. Okay.
Yeah. Right. So the point to note is that in any serial run, it must respect this partial order, right? Because this did a read and this did a write. I have no way of commuting those two events. So read must always occur before the write. Okay. And similarly, if I draw in all the other edges, I know that this read should occur before this write, and I know that these two events are also related because these belong to the same thread. They're different transactions, but they could be local memory in the thread which forces this ordering. So you may not be able to commute these two transactions. It wouldn't make much sense. Okay. Now the crucial thing to note is that if this read has to occur before this write, then in any serial run, this whole transaction has to occur before this transaction. Right? Sorry, question.
The yellow transaction was from a different thread, but it started at the same time. I mean, would you take it as a dependence relation? I mean, are you looking at conflict serializability or strict serializability?
This is conflict serializability.
But in the specification, I mean, you would not create strict serializability.
So what we do not handle is actual simultaneous events that happen in the run.
Yeah, but suppose there was thread 3,
Yeah.
and this yellow transaction belonged to thread 3, but it started strictly after the green transaction.
Okay.
So would this be a serializable?
No, that would be okay because there would be this edge would not be there, and that will be okay. Yes. Okay, so the crucial thing to note is that if this read has to happen before this write, then this whole transaction has to happen before this whole transaction, right? So that's a very simple observation, and that's all you need to do this monitoring, is that you know that you just keep this ordering between transactions, which tells you how you must order these transactions, right? So the constraints are that T must occur before T prime, and again we have this constraint that T prime should occur before this transaction. And this transaction should occur before T again. Okay? So, and that is impossible, and therefore this is not conflict serializable. Right? So again, you keep the ordering between transactions, which are entailed by the run, right? And you check whether there's a cycle in this ordering. If there's a cycle, then there's no way to actually serialize it.
Actually, I have a question about the basic definition, not about this method.
Okay.
So there are these events that are happening in the system. Presumably, there's some state of the system which these events transform as they execute.
Yes.
Now this whole story, does it depend on these events being deterministic? Meaning that they are deterministic straight transformers?
So I would say no, because as long as the non-determinism is manifest in any other ordering I give you. So for example, if I started to permute this and that non-determinism was manifest, then it is okay, because then there will be a serializer that will be realizable as well.
Okay, I think this should be taken off now.
Okay. So, but let's just assume it's deterministic for now. Yeah. Okay. So here's the definition of a conflict graph. You have one node per transaction, and each node is labeled with the set of actions you did in the transaction. These are only on the global variables. Okay, so you have to remember all these events that happened, and you have an edge between two transactions if there are two conflicting actions, dependent actions, and the dependency arrow is thrown in according to the arrow of time. Okay, and if there is a cycle in this graph, then it's serializable. Otherwise, it's not. This is a sound and complete algorithm to maintain to check serializability. So we immediately get a monitoring algorithm, which is accurate. What it does is essentially it constructs a conflict graph on the fly. You keep track of, you can instrument the program so that you keep track of this graph on the fly, and you report atomicity violations if there is a cycle. Okay. So here's a problem with the whole thing is that within a few seconds you can execute millions of transactions. Okay, in a typical run, if you just mark, let's say, methods to be atomic, you can have on normal examples you'll have hundreds of thousands of transactions happening, right? So it is not practical to store the exact conflict graph all the time. Okay, so the question is, can we get rid of some transactions in this conflict graph, right? So maybe we don't need transactions, the nodes for transactions which took place long time back. We can just get rid of them, right? So here's an example, right? And I have I construct the conflict graph, right? So I have this. So this is just an example showing the conflict graph. Sorry, I'll come back to my problem later. So let me skip these. So this just shows for this example how this conflict graph works and how you actually find a cycle. Okay, so here's an example. So what I've done here is that again this is the run, right? And I've monitored this run, and I've produced this following conflict graph. T goes to T prime because this read occurs before this write, and since this write occurs before this read, I must have T prime before T double prime. Okay, I have this, and then I notice that the second transaction actually ends. Okay, so this T prime is a transaction that is complete. Okay, it's over. Can I do something about it? Right? So do I still need to remember T prime? Okay. So any guesses?
So you're asking if T prime can be eliminated and you can short circuit from T?
Yeah, right. So I can maybe I need the edge from T to T double prime.
I mean, what if there is somebody else who accesses one of these variables that T prime is accessing?
Exactly. So is that so the answer is actually no. You cannot remove T prime, and the example already does that. Is that if you have a read Z here, then actually it's a problem if you eliminate T prime. So for example, if I short circuit this and take out T prime and add instead an edge from T to T double prime, then if I do this read Z now, then actually in the actual conflict graph I would have gotten a cycle because T prime to T there's an edge, right? And I would not get this now because this has only a read Z and this has a read Z. There's no other edge you add if you had only T and T double prime. Okay.
Sorry, for the definition of the transaction is predefined, like for the first thread, from read X to read Z, is predefined or is it dynamically defined?
It's dynamic. We're just monitoring a run.
Okay, but how do you break down into two transactions so that you will not have these cycles? will be a set.
So the idea is that these are two reads which are happening very close together, and they've been marked to be in one block. Let's say in a method sequence.
Okay. But what I mean, the method, could you break down into two transactions?
I mean, you could. I mean, if you
break down this cyclic conflict graph, right? Yeah.
Right. But that's not the. I mean, the idea is that there's a logical structure behind the sequential part, and if you just break it into two transactions, it's the whole point is to find an error using this. And, okay. So to summarize, I cannot just simply take off a transaction just because it's over. Okay. And amazingly, this is an error in a paper published by Allure, Macmillan, and Peled. And this went all the way to a journal version. This error was completely not noticed. This is more than 10 years back. Okay.
In this example, if it was a right z, then it would have been okay. In the t double prime, the right z.
Yes.
It would have been okay to eliminate t prime.
But that's not. So, for example, I could have had another thread which does this read y and write y, and that need not have any z at all, and still everything would have been okay. So it's not about the reads and writes. So it turns out that this is a very well studied problem in database theory. There's a paper by Hatzilakos and Yannakakis called Deleting Transactions, which actually goes about finding safe conditions under which you can remove a transaction from this graph. Okay. So we looked at this, and when we said, can we implement this deletion policy? And it turned out it's very complex. So you have to keep a lot of information about deleting transactions, and it's not really practical to implement this. Okay. So part of this work was about 4 months of digging into database literature, trying to figure out what they knew about this problem. Unfortunately, we didn't know much about database transactions, and we didn't want to invent this thing. I think partly because this was the golden period of database theory, where people were of technical competence way more than mine have worked on this problem, and I refused to believe that they didn't have an answer to this. And I didn't want to come up with ad hoc solutions to this problem, which unfortunately a lot of people do that. So I didn't want to do this at all. I wanted to really see what people knew. Okay. So we read a lot of papers, and we found this paper by Casanova in 81. This was after Papadimitrios' textbook, so the Papadimitrios' textbook didn't have it. So it turns out that this whole obsession about deleting transactions from this graph is the wrong idea. Okay? You should not go about deleting transactions from this graph. It's way too complex. Yeah, in fact, Hatzilakos and Yannakakis proved that figuring out whether you can remove a transaction from this graph is actually NP hard in the size of the graph. Right? And if you're going to do this every time a transaction completes, there's just no way it's going to scale. All right? So there is, in fact, a very simple technique where you do not examine the graph. You have a very simple update operation which does not remove the transaction simply by introducing transitive edges, but actually does something a little more clever. Okay? This is buried deep in this completely hard to read paper by Casanova. It's probably his thesis, right? So I must say that we had to take this, strip out a lot of information which is required, because in database literature, what you also have to do is roll back if there's a conflict, right? So there is a lot of information that needs to be kept in order to do the rollback and do it effectively. You need to keep more information. So actually, you have to get rid of all that information, because we are not interested in rolling back. We're just interested in seeing whether there's a violation. And then there is this other notion, is that in the database world, everything is just a transaction, and the transactions are not related to each other in any way. Whereas we have this relation that a thread has a sequence of transactions, and the transactions are sequentially related. Right? So it's not a pure database world. So we had to adapt this whole algorithm to this framework. And what the algorithm does is, instead of keeping the set of events that happened in a transaction, which is the schedule set, for every transaction you keep the schedule set, which is the set of events that happened in T1, as well as a conflict set C1. Okay? And the idea is this, is that if suppose T4 is an event, is a transaction, and let's say T4 gets over now, it's completed, right? Then what I do is I look at its predecessors and its predecessors and successors, and what I do is essentially do the transitive closure. So since this node is involved in this edge, in this path, I need to keep this path. So that idea is a good idea. Okay, and I remove these other edges that come in. But what I do is, so T4's predecessors were T1 and T3. I add the S4 and C4 sets to the conflict set of these two transactions. Okay, so the idea is that if there were going to be edges later in this graph, then those edges have to be outgoing from this. It can't be incoming to this, right? They're outgoing from this. Those events will depend on S4, the things which happened in S4, and you need to summarize this by taking this and putting it in your conflict set and remembering it in its predecessors so that you catch all cycles. Okay. By the way, these theorems are very hard to prove correct. It's including Yanakakis' proof of deleting transactions is very hard to prove correct. It's a very subtle involved proof.
So the reason in T1, for example,
yeah,
there was a C1 to begin with was that everyone C1 starts out empty, right?
Empty, yes.
And C1 got introduced because there was some other successor of T1 which got deleted at some point.
Yes. Okay, so let's look at an example. Yes.
Roughly speaking, so this has pretty much the flavor. Part of it has part of the flavor of clock vectors, right? So how does it relate to that? Because these are relatively easy. Well, it's tricky, but it's not that.
So when I come to causal atomicity, I'll talk about clock vectors. And I do not know any clock vector algorithm for serializability. I can explain the reason as well, but basically, suppose you had two transactions, and there were dependence edges this way. This is not serializable. There's no serializable run. But if you think about the clock vector, it has the individual clock vector has no information that it's actually not serializable. And so the point is that if you had, and we'll talk about this later, is that if you had a run which was not serializable because of this kind of pattern, then you can in fact do clock-based analysis to check serializability.
Where are you going? You haven't shown this cartoon. You haven't shown how to use these conflict sets.
I have not shown. I've not shown how to use this conflict sets, but I'll just do it through an example. So I'll come back to the space bound later. So the idea is this. Let's go through the same example. So I start with T, and I have the schedule set and conflict set to be empty, right? And then I do a read, and that gets added to the schedule set, right? And so then the T prime begins, and I initialize its sets to empty. It does a write. I throw it into the schedule set, and there's an arrow because of this thing. So when I throw in an arrow, what I'm looking for is whether there is any dependence between S union C, this S union C, and that S union C. Okay. So now I do a read Z, which what it does is it just adds that on to this thing. This transaction ends, and here's the crucial part: is that I'll take this set of scheduled events and add it to the C set here because of the predecessor, right? Okay. And now, so this diagram is a little wrong. So all these events are also tagged by the actual transactions that did those events, which wasn't marked, and because of this keynote problem, I couldn't change last night, right? So essentially, these events are tagged with T prime because they're all T prime events. Okay.
Oh, you mean like even when you put them?
Yes.
When you do that merge operation, you keep track of the ID.
Transaction ID. I keep transaction ID and the actions that took place.
I mean, then you're not really saving. What space are you saving in that case if you're keeping the transaction ID? I mean, it's just like having a separate node, no?
No, it's not. It's not the transaction ID. It's the thread ID.
Ah, okay.
It's a thread ID. So the reason you need the thread ID is that because these two transactions are related, the next events that happen here have to be dependent on these events that happen here, and you need to remember that. Okay. So that will happen now because if when you do a read Y, what happens is that this read Y is dependent on this read Z because they both belong to the same thread. And so you'll get, again, an arrow from here to here. Okay, and when you do a write Y, you will get you will add it to the schedule set, and there's a read Y and write Y, and there will be a cycle.
Just a off-the-wall question, but if you were looking at strip serializability, then you do not need the thread ID to. I mean, when you
the thread ID is because we are working in a world where there are sequentially related transactions, which is not usually true in databases. I'm not capturing the local state of the thread, so there's no way to assume for me that these two transactions can be commuted.
Yeah, but the only reason you need the thread ID is because two transactions, if they come one after the other, have a conflict if they are from the same thread, but they do not have a conflict if they are from separate threads.
True. So I could do a slight modification where when I create I wait for this event before I create the new, before I throw away the old thread and keep that. You can do such an optimization. Okay, so the beautiful thing about the summarized config graph, in case you haven't noticed, is that I do no checks. I don't go about searching this graph for any great property, right? I don't look for things which I can throw away. I always throw away the transaction. But what I do is I imbibe these events in the old transactions, and I don't try to throw away these events. Okay, it's not a formal theorem we have proved, but we can show that every this information that is kept by this summarized config graph is absolutely essential, in the sense that if I have two summarized config graphs which are different, then they have distinct futures, in the sense that if you give a future to one, it should say serializable, whereas the other one should not say serializable. This is like a Myhill-Neuro theorem for streaming algorithms, right? So the idea is that if you're reading it in the streaming fashion, this is absolutely the only information you need to keep and which you can keep. You can't do less than this.
There's still an awful lot of information because you're keeping track of every single event that happens in the execution, right?
Right.
All you've eliminated are these nodes.
Yes.
So I'm not sure in the how much optimization did you actually achieve in the end?
No. But when this transaction ends, all this thing will be thrown away. If you didn't have predecessors, for example, the whole thing will get thrown away. It's not like you keep accumulating everything.
But I mean, transactions are going to have predecessors all the time, right? Why won't they have predecessors?
No, if they get completed, they'll get thrown away, and then you'll have no predecessors, and you'll get thrown away.
Right. You are transferring information from the transaction to the other conflicts. So sort of summarizing
Only to the predecessors. See, the point is that if I've committed, but a transaction which I depend on is actually pending before, then I need to keep track of this set in that transaction. That transaction has to keep track of me. That is essential. But once that transaction gets over, if it doesn't have any predecessors, it can just throw away all the events. Okay. Okay. So anyway, but this is the best algorithm you can get. It's sound. It's complete. It's a minimal amount of information you can keep, and it is at least better than trying to throw away transactions, which would be very hard. Yeah.
So if you actually prove this theorem that you need this structure,
Yeah.
it's like a lower bound on the
complexity of that Atomicity
Yes.
function.
Yes. It is.
does there exist such a proof?
Yes, we do have a proof, but we didn't write it in the paper, so there is such a proof. Okay, so let's go back to what the complexity of this is. So from an unbounded amount of memory which I needed to keep using conflict sets, I've bounded this completely, this information, so they have a space bound of n squared plus nk, where n is the maximum, after I do a run, if the number of active transactions is n, and k is the number of entities I've touched, right, then, and if these are bounded, then I have n squared plus nk, right. And this will be useful later to actually show things. K is the number of entities. So every transaction, I'm remembering the set of events which happened. So all the events that you've touched.
N is the number of threads, K is the number of events.
N is the number of active transactions.
Okay.
So threads can also complete. You can have dynamic creation of threads. If threads complete, that's fine. As long as the number of active threads in the entire thing at any point is bounded by N, this will be bounded. Okay, so here are some example experiments. Okay, so we tried this on some benchmarks, the Java Grande benchmarks. So SOR, LUFACT, and Ray Trace are Java Grande benchmarks, and these are benchmarks which people typically use in this literature. So the SOR and LUFACT are data parallel algorithms which essentially take a matrix. Depending on number of threads you have, you divide up the matrix and you actually perform computation on them. So what happens in these algorithms is that usually every node in the matrix you compute the node for this using the nodes, the values at these nodes. You compute the value for this. And the actual form of synchronization is separation. So what they do is use a checkerboard kind of separation. So the idea is that you have you divide this matrix into a checkerboard. So you think of this as black and white, right? And if a thread is responsible for a set of rows, and what it does is it touches only the black ones, right? And there's a synchronization after all this which says that now the threads can go and do the white ones. So there'll be a thread here and a thread here which works on the black events, and they will then go and do the white events. And by this, they make sure that they don't interfere with each other. Okay. So that's the SOR example. LUFACT is similar. Ray Tracer is actually an example where the number of global variables is very less.
The conflict is on the edge, basically. So you want to make sure that you never have them working on things which share the same edge.
Right.
I see.
Share the same. Yeah.
Share some edge.
Yeah.
Okay.
The elevator is an example where an elevator is modeled. For every floor, you have a process, and anyone can press something, and so on. It's a fairly popular example. Traveling salesman problem is actually a concurrent version of traveling salesman problem implemented, and of course, it's not. I mean, it's an NP complete problem, but it's a concurrent implementation. Okay, so these are so we observed runs and I'd like you to see the number of runs. The number of runs really becomes large when the number of so the length of the run becomes really large. And here is we implemented both the conflict graph algorithm, which kept all the conflict information, as well as the summarized conflict graph, where we threw away all this information, right? So as you can see, for example, if you have 50 threads, you have 15,000 transactions and 3 million edges between these transactions.
So where did you get the Atomicity specifications?
Yeah, I'll come to that. Okay, let me. So essentially, these are for SOR and LUFACT. They were essentially spawning threads which work on different parts of the matrix, and we just marked the whole thing as atomic. So all parallel forks and joins, we just consider the whole thing as atomic. And I think that was the right intention in these programs. And for these other things also, there were similar things. So essentially every flow, whatever it does, is an atomic.
Check every possible run?
No. So we do only one run. So we're just looking at one run and checking whether it is atomic or it's serializable or not.
For concurrent program, the real problem is that there could be some certain interleavings which lead to
Absolutely. So I'll come back to that.
Okay.
But if I don't know how to do even one run, I think it'll be hard to do many runs. Right? So here, so if you notice this, it's very surprising. For example, in SOR, we didn't even finish for 50 threads. There's just too many nodes and edges. But the summarized conflict graph has 17 nodes, the number of nodes grows with the number of threads.
I got a question. Supposing you take the first row
Yeah.
and 3 threads, 680K. If you run it without your instrumentation, how long does it take to finish?
118 seconds. That's the CG is the.
CG is not without any conflict graph. No, what
without it, it's a second. We're not even comparing the overhead here. So I must also say that the way we implemented this is to actually take the run, write it onto a file, instrumented it so that all the accesses were written onto a file, and just examine that file. Okay, so it's not an inline.
So then, what do you mean that it didn't even finish? You mean that you couldn't even generate the file?
No. The conflict graph. You construct the conflict graph, and you can't even generate the conflict graph. It's just too much. It just ran out of time. It took more than 8 hours to.
I see. So you were able to download all the events into a file on disk.
Yes.
But from that file on disk, it took more than 8 hours
to even compute the conflict graph. Yeah. And then so that time really says how long it took for doing the conflict graph and doing the cycle checking. Okay. But the surprising thing is that there are 0 edges here. Okay. There are some number of nodes which grows with the number of transactions, but it's a correct program. There was no violation found, and actually you don't have to have any edges in this graph, right? So it's an extremely small graph.
How does it relate to the case in the previous slide?
Which relate to the so the number of transactions is n. So we don't have the full figures. These are, I think, 500 by 500 matrices. So they were about if you have 50 threads, there were about 100 transactions each, and yeah.
I don't understand the column. So why do you call CG and then you have SCG? What is SCG?
Summarized conflict graph. We call this new thing.
You start putting all this
information is a summarized conflict graph.
So it's 3, 0. Okay, so conflict graph is if you just do the vanilla algorithm without doing anything, no deletion, nothing.
Yes.
And then you can verify the run. In that case also, that takes 118 seconds.
Yes.
And then if you do the business that you have, it takes only 0.5 seconds.
Yes. And it has at most 3 nodes and 0 edges. At any point along this run, I have at most 3 nodes, and I actually have no edges in this graph. So to answer your question as to why this might work in practice, I think it will work well in practice because the summarized conflict graph kind of tells you what the real interaction pattern is, and it tends to be very small for correct programs. Okay. So you can look at the number of nodes and edges. So here there's a kind of linear relation. So 50 nodes and 49 edges, which is almost like a linear set of edges is what we have. Okay.
Because you have, say, like 600 transactions, right?
Right.
So initially, even though for the ICT, you still need to allocate that number of nodes, right?
So what we do is it's an online algorithm. You take these transactions, you read event by event, and you keep a summarized conflict graph. Mm-hmm. So you throw away lots of things even when you're processing this.
Yeah, I agree. In the middle, you need to throw out everything, just have 3 left. But at the beginning, right, you need to create a graph for every node.
No, I don't create any graph. I just have the run, and I read the run one by one and create the graph on the fly. So it's a completely streaming algorithm. Okay, so then we notice that the space bound, the fact that the space is bounded by the number of threads and number of entities actually gives you a model checking algorithm. And as far as I know, this is the first model checking algorithm for serializability checking. That is that if I gave you only finitely many threads and finitely many entities, I don't think it was even known that this was decidable as to whether you can model check that all runs are serialized.
I mean, there was this incorrect result, right?
Yes. So there's this wrong proof in the literature which tried to do that. Perhaps that's why it wasn't studied at all. So the model checking. So essentially, what we do for model checking is that you can build an automaton which accepts a set of all serializable runs by essentially monitoring every event. It will keep track of this graph. And this monitoring, since it's space bounded, you get a finite automaton, and you can actually do an inclusion check to check whether all runs are contained in all the serializable runs.
Just to make sure I understand, so you do not allow cycles correct?
In the
finite state model.
No, we have cycles.
So you're saying that you have a finite state machine.
Yes. Let's say a Boolean program which you've extracted out of this, out of some program, a Boolean model, and you have a finite number of threads only and a finite number of global entities, and you want to know if all runs are serializable. Yes.
No recursion here. It just means finite, basically. Finite state.
Yeah, there's no stack for.
So what you try to check is if the semantics of your program is correct or the implementation of your semantics is correct. So like if I write atomic here and look at this program, it's correct. But by implementation this atomic block, you probably will interleaving them.
Yes.
And you see the...
Right. So the semantics of your programming language, it completely ignores your atomic annotations. Right? You have implemented, your intention is captured by these annotations. And you're trying to check, at least for one run, you're trying to check if that all those atomicity violations are okay.
So you're checking the underlying transaction memory implementation?
There's no transactional memory implementation. It's a pthread, Java, whatever implementation. It's not a transactional memory implementation. Okay, so this is where I shift to the other. Okay, so let me briefly tell you about causal atomicity. This is this other notion, which is different from serializability, which we introduced in CAV 2006. And this is a very simple notion of atomicity, which essentially says that suppose you have a transaction, and I have two events, E and G, and I have this in-between event F, which occurs in another thread, and this F event is actually causally later. There could be many events which lead to F, but F is causally after E, and G is causally after F. Then clearly this is not serializable, right? And this is what causal atomicity says, that if you find such patterns, then they are not serializable. Now it turns out that this is not the same as conflict serializability, because what this really is saying is that every transaction is individually serializable, okay? Which essentially says that if you take a run and you pick any one transaction, I can serialize that transaction for you, okay? I can't do the serialization of all transactions simultaneously, that I do not assure, but certainly I'll be able to pick any one. You pick any transaction, it is serializable, okay? So it's a weaker notion than conflict serializability, and it turns out that. So when we first published this paper, there was a lot of questions about why not do serializability, why this weird notion. But actually it turns out that most papers in the literature actually do that, and they simply do not know that they're not doing conflict serializability. So they believe that they're doing conflict serializability, and if you look at the actual code, they're actually doing only causal atomicity. Okay. It's a subtle difference between causal atomicity and serializability, conflict serializability. Okay, so how hard is it to actually monitor causal atomicity? So in general, if you first think about it, if you didn't know all this database literature, you would first think that it's very easy to do causal atomicity because you can do this using vector clocks, which is something we are more familiar with. So the idea is that when a transaction begins, it will take a new timestamp. Right? It's a local timestamp. It'll update its local timestamp, take it, and everything that it writes to, it will write this timestamp onto. The other threads will keep track of this timestamp and pass them on. And if you read your own timestamp during your transaction, you can say that there is actually a violation. Okay? So it's a very simple way to implement causal atomicity. But this does not give you model checking algorithms, or if the number of transactions gets very large, we still don't know how to do it because the number of timestamps, you have to have it unbounded, and the garbage collecting on timestamps is not clear how to do. We do have some new results. There is yet another theory of asynchronous automata, and a very deep result from this theory says that bounded timestamps always suffice. Is that you don't have to, you can distributedly monitor all your timestamps and start reusing them. Okay, so so it's a very nice result. The update information is actually very simple. It's a hard result to prove, but the algorithm is not hard, right? But we still think it's a bit of an overkill for multi-core because you do have access to global memory which you could use, and just being very stubborn about using only local memory can be harmful. I mean, maybe you will get more efficiency if you do some global amount of information.
Apply to data race detection as well when you're doing vector plots. So what is the theorem actually?
Yeah, it should hold. I mean, it holds for what is called any general regular property that you're checking. It holds. So definitely it should hold, and I don't know if anyone has implemented it.
So actually, there is a data race detection algorithm called Goldilocks, which doesn't use timestamps, but it uses another representation that is guaranteed to be finite. But I don't know what that connection of that is. Maybe that's.
But that's for data races.
Okay. Maybe that's just an instance of it.
Maybe. So what we have in the end is that we have two robust notions, serializability and causal atomicity. They are quite related, conflict serializability and causal atomicity. And we have now robust mechanisms to monitor them. And as our friend pointed out, we don't know what to do with this, right? We have not done anything particularly with it. So the only thing we have done is, So in these examples which we did, we do get errors. So for example, ray tracer uses only very few bits of global memory, which it actually has synchronization with, and there's actually a serializability violation, and it turns out to be a real error. So you can already use this to find errors in programs using this notion of atomicity. But the more interesting thing is actually to so first what we want to do is develop an automatic transformation technique for programs so that they can self-monitor themselves, so that we can give you an atomic exception which tells you that there's an atomicity error detected, and you can use this either to test from the outside, or you can use it to actually change the course of the program. Right? But the most interesting thing which I'm working on now is to apply this to concurrent testing. So the idea is, in concurrent testing, the way I look at the problem is that you're given a test harness, and this is very similar to chess. You're given a test harness, and you'd like to test all possible executions on the test input, and this is currently too expensive. So my thesis is that one shouldn't try all interleavings, which is the same as chess. Chess advocates doing bounded context switching runs only, and the idea is that will manifest most of the errors. But the idea here is that you can try looking for runs which are non-atomic. So what we are looking for now is that how do you look only for non-atomic runs, non-serializable runs? The idea is that
if you have the set of all runs and you partition it in the set of atomic runs and the set of non-atomic runs, what do you think is the relative ratio of the two subsets?
Oh, that'll be hard to guess. Yeah, but
what's your conjecture on that?
But I think if you look at partial orders,
okay.
I think so. A non-causally atomic run is just one run, right? And I think it'll be. I don't know how much it'll be. I really don't know, because one of the problems is the actual application space. In these kinds of examples, I think that it's a very small fraction of the entire set of interleavings.
Which is a small fraction?
Only the non-atomic runs.
The non-atomic runs are a very small fraction of the set of all interleavings.
Yes.
I see.
Right. But that question requires that you have that atomicity specification. Right? Without that,
Absolutely. But that's why I like this approach, is that I do not report to you that there was an atomicity violation. Right? What I do is I find a non-atomic run, I run it against a test, and see whether the test harness satisfies it or not. If it satisfies it, it's fine. So I can guess using, let's say, all methods are atomic. I can just put a blind guess, and I will not give you false errors with respect to that guess. I'll give you errors only with respect to the test runs. So here's actually a simpler problem we're looking at, is given a single run, can we predict what runs that run entails and whether those runs, whether that space itself has any non-atomic runs. Okay. So there is work on this area. There's Wang and Stoller have done a predictive analysis which is not complete for conflict serializable violations. Grigore Rosu also has predictive analysis for causal atomicity. Again, this work says atomicity, but actually what it does is causal atomicity. We also have some partial answers to this question. In particular, if there is very little concurrency control, a very, very fine kind of concurrency control, then it's easy to do. So if there is no concurrency control, which is actually true in these examples where the data is partitioned, you actually have a polynomial time algorithm to test whether all the runs which lie around this run are non-atomic. Okay, it's a very simple cycle detection algorithm which will tell you whether this is true. But what we are more crucially looking at is a model of causality. So given a run, how can I accurately predict which runs are entailed by this run? And there's significantly less work done in this. And the ordering of causality which I presented in this paper, in this work for checking serializability violations, is not that order. Okay, there are much more liberal orders where you can derive more runs. So let me move to related work. So the causal atomicity was introduced by us in 2006. Serializability is an old notion, and dynamic and runtime monitoring were done. So runtime monitoring is this work, and there's a dynamic predictive analysis by Wang and Stoller. So they also worked dependent on this notion of Lipton transactions, which is a kind of over-approximation of serializability. So Lipton transactions, if they are Lipton transactions, that will imply both causal atomicity and serializability. So it's an even weaker notion. Yeah. So the Wang and Stoller work is actually quite interesting, and what it does is essentially keep track of this conflict graph and tries to do analysis on that. So it works. So they don't say this really in their paper, but it really works only for nested locking mechanisms, right? So if they're interested in Java programs where locks are well nested, and in fact they have other assumptions like non-dead locking and so on. And their analysis really works only for 2 threads at a time, right? So it's sound and complete only for 2 threads. If it's more than 2 threads, it's not really accurate. So for the example in the SOR a benchmark, if I scale the number of threads to 50, it turns out that the algorithm does not scale at all because the graph that they keep is much larger. So I think one thing which we kind of realized over this work is that a streaming algorithm, just sticking to a streaming algorithm where you maintain only the information of the past that you absolutely require, is a very good heuristic to build actually efficient algorithms. Okay, it can be polynomial on the entire graph, right? But a streaming algorithm usually performs much better, and we have seen this in other contexts as well. Okay, so there's this chess work by which bounds the number of preemptions. There's also work by Kaushik at Berkeley where he tries to kind of actively guide the run to get serialized atomicity violations. But he also uses randomized. He doesn't do systematic analysis, but uses randomized ways to explore this space. And actually, he also does causal atomicity. Finally, there's this piece of work which appeared in PLDI 08, and it's concurrent to ours. So what they did is that they use the conflict graph. In fact, for the ours and their work used the conflict graph for the first time. They use the conflict graph to detect serializability violations. They don't call it the conflict graph. They don't refer to any database literature. And I don't know whether they found it by themselves or not. They have a very vanilla deletion of transactions.
Is this wrong? Does it suffer from the same bug that was in the Allur-Macmillan corrected?
No. So their deletion policy is correct. So the vanilla deletion of they do have a vanilla deletion of transactions. So they go back to this whole transaction. I think it's a very natural idea which you think of in the beginning. So they do that, and they do it heuristically. And actually, this vanilla deletion is also present in the old work, right? If you look at Hatzilakos Yanakakis 76 paper, it already has this vanilla deletion as one of the propositions first in the paper, right? And that vanilla deletion does not allow you to get bounded monitoring algorithms. It's completely unbounded. You have no idea. You can come up with trivial examples where the whole space blows up. It actually has a blame assigning notion, and that is actually similar to causal atomicity. So one of the things which I hope happens is that people start using at least the same vocabulary as, it need not be causal atomicity. You can call it something else, not because it's mine. But we need really a common way to talk about these access patterns and interaction patterns. Otherwise, I think we'll do a lot of work again and again. Thanks.
I got a question. So why for these programs, these data parallel programs where there's more or less static partitioning of data, why is the number of non-atomic runs so small? I don't have the intuition for it.
Why is the number of non-atomic runs
that's the point you were making,
small?
right?
Yes.
Why is that?
Because they have very few places where they can actually interact. There's this borderline places where they can interact, and that's it.
I mean, this is sort of vague, right? Because supposing, right?
Yes.
Roughly the idea is that a non-atomic run is buggy. Then your statement could be taken roughly to mean that there's a large space of erroneous execution, there's a large space of execution, but only a few executions are erroneous. Is that all there is to it, that statement?
No. So that space is not the wrong executions is even much smaller, I would believe.
I see.
Right.
So it's like this.
It depends also on the spec. What is the atomicity? If you assume by default that everything is atomic, etc., some program you could basically find lots of. I mean, every run is going to be violating that assumed spec, generic spec, or inferred spec, and so.
Because this is not just a heuristic. There is no golden notion of atomicity.
Yeah.
Right. And it also depends on the application. If your application
Absolutely.
data parallel,
Yes.
right, then almost all executions would be atomic, right? Because there would hardly be any
Communication.
I have a high-level question about this, the other Macmillan thing, and maybe you explained that at the beginning, and I missed it. But so the problem there that they wrongly proved that serializability was undecidable for
decidable.
Was? Sorry?
Decidable. They proved it's decidable.
You proved it's
Well, they wrongly proved it's decidable. I don't know. Wrongly proved is strange, yeah. But they had a proof saying that it was decidable, and the proof was wrong.
So Madhu's result and their result is exactly the same complexity. P-space complete, but his proof is correct. Their proof was wrong. That's what you're saying.
And so that sequential consistency was like undecidable.
Yes.
And what was again the linearizability?
Was decidable.
So did you check
what was the complexity? NP.
I don't remember.
Something. NP complete, right?
I don't remember.
So did you check those two proofs? Because I've been using that sequential consistency and decidability for a while.
I haven't checked.
But sequential consistency is easy, right? It's because you have like in these Mazzucato traces, you can have A and B and Cn. And I mean the language generated by computing this operation is not even context sensitive and things like that, right?
Okay, I don't know.
So one of the things that the database guys have sort of realized is that this notion of transaction or atomic sections, they are very low level. They work at the level of memory reads and writes. Right? That is not a very good abstraction to define correctness of your transactions, because you can have these high-level serializable actions, right? If you have a list, right, the list is implementing a set. Right? So have you thought about ways in which you could define these kind of abstract notions of atomicity?
Right. I think so. So there's notions of purity and other things try to do that. There have been some attempts to do that. There's no so once you start reading the actual operations that take place in the program, I think there is more hope that you can do something. But I think from what I see, it's more of the belief that you'll come across certain patterns and you'll say, you know what, that looks like it's non-atomic, but actually it is atomic. Kind of patterns you might come up with. Yeah, but I don't know whether that will yield robust and simple to understand algorithms like these. It might be very hard.
So I have maybe an answer to that. I have a paper called Transactional Boosting, where what we do is the individual events are not memory read and write accesses, but rather some more larger scale logical operation. And so we show that there's a way to use some notion of abstract locking to generate strictly serial.
Open nested transaction work?
No, it's kind of in contrast to open nesting transactions. It's called transactional boosting.
So this is basically a better implementation of STMs. This can use some higher level commutativity.
Yeah, and it just throws out the whole concept of monitoring read-write sets and instead just keeps track of high level notions of commutativity.
Mm-hmm.
Yeah, so as long as the programmer knows what commutativity is.
What is this paper? What's the title of the paper?
It's called Transactional Boosting. It was in PPOP this year.
Okay.
So the idea is that you have to declare which operations are commuting. Okay. So this kind of work has been done in other areas as well, in actor-based computation and stuff, where you can declare these to be explicitly commutative, and you can then reason with that.
So, but the thing is that in your system, supposing these commit, so the programmer presumably gives some annotations, which says that this operation commutes with that operation. How do you trust those annotations?
Yeah, you have to. I mean, so a separate issue is whether or not you can prove that they actually are correct.
Cool. All right, let's thank the speaker again.
Thank you.